Okay, this is verifying trig identities, and what I'm giving you here are four of the most basic but also some of the more complicated problems that we can run into and ways that we can get around and use these methods to solve. So the first one I have is rewriting with sine and cosine. That's the most basic thing you want to try. You always want to make everything in terms of sine and cosine. Not always, but usually it's a good way to start. And then you probably have to use some fractions, either multiplying, dividing, or adding or subtracting. So we'll start with that. We also have using factoring. Usually this coincides with the Pythagorean identities, which we'll talk about. Number 3 is working with fractions. It's almost always a necessity. Like I said, multiplying, adding, dividing, subtracting. Knowing how to do that work. And the last one is using conjugates. That's usually like a last resort, but sometimes it actually makes some of the problems pretty easy. And that's when you have two binomials and you're multiplying them, but one of them you're adding the same two things and the other one you're subtracting. It's a plus b, a minus b. It's also the difference of squares rule backwards. Alright, but we'll talk about each one as we go. So the first one we're going to do is using sine and cosine, rewriting, and then working with your fractions. It's very, very important you know how to do this. Everything builds off of here. So we have sine times tangent over secant plus cosine times cotangent over cosecant, and I forgot to write it in here, but the answer to that is actually going to be 1. And we're going to work through all our rules and simplify that down. And we're going to do step 1, which is rewriting everything in terms of sine and cosine. So the sine stays the same. Tangent, we should know tangent is sine over cosine, or sine divided by cosine, so we'll write sine divided by cosine. Real simple. And the secant is 1 over the cosine. It's a reciprocal of cosine, so it's 1 divided by cosine of theta. Alright, now we're going to do the same thing over here. We'll go a little quicker. Cosine of theta. Cotangent is cosine over sine. So we're going to write it like that. And the cosecant is 1 over the sine. By the way, when we're verifying, we already know what the answer is. You can't use it like an equation. You can't add or subtract to both sides or multiply both sides by something. Basically, you're working on one side only until you get it to equal that other side. So we're going to keep messing with all this stuff until we get 1 out of it, hopefully. So as we continue through there, you're just going to do the math. Sine times sine over cosine is basically over 1. Sine times sine. Sine squared over cosine. Pretty simple. And we're going to put that over, and then we have 1 over cosine. So I'm just simplifying the fraction. And then the same thing here, cosine times cosine. Remember, this is over 1, so cosine times cosine is cosine squared over 1 times sine is, sine of theta. And then the bottom will leave that 1 over sine theta. Okay, looks better, not where we need to be, but it does look better. So we're going to continue on that path, and we're going to do a complex fraction. We're going to do our favorite copy times flip. You're going to copy the numerator exactly the same way. And you're going to multiply the denominator by its reciprocal. So 1 over cosine turns into cosine over 1. And then the same thing over here. We're going to copy the numerator times, and we're going to flip the denominator. There you have it. And we're basically about done. These cosines will actually cross cancel or cross divide, and we're going to be left with sine squared of theta plus cosine squared of theta. And if you know your original trigonometric identity is the Pythagorean identity is sine squared plus cosine squared equals 1. And this checks out with what we started with. We wanted to be 1, or we wanted to equal 1. We've got it to equal 1, so we're done with that problem. Alright, so that's a crazy one, but that's what we do. Number 2, we're using factoring again. We're using factoring this time, but we're going to use Pythagorean identities to do it. So we have tangent squared over secant minus 1 equals secant plus 1. And again, we're not going to work on this side unless we absolutely have to. We're not going to multiply it. The easy way would be multiply by secant minus 1 to there, but we can't assume equality, so we're actually going to rewrite and substitute and work our way down. So this time I said we're going to use factoring, so let's do that. First and foremost, the Pythagorean identity, if you've forgotten it, you have, I'm going to write it in a different color, we have 1 plus tangent squared theta equals secant squared theta. You have to utilize that, so we can rewrite this by subtracting 1 from both sides, and we get tangent squared theta equals secant squared theta minus 1, just by rewriting. So over here we're going to make that substitution. We're going to rewrite as secant squared theta minus 1 over secant of theta minus 1. And a lot of people are going to make a mistake here and assume that we can eliminate a secant and a 1 and a 1 or something like that. You cannot do that yet until you factor. If you know your difference of squares, the difference of square rule, I'll write it in pink. It's x squared minus y squared equals x minus y times x plus y. It's factoring binomials, subtracting two squares, you take their square roots and you write a minus and a plus. These are called conjugates, which we'll also talk about later. So we're going to do that here, and we're going to write secant of theta minus 1 times secant of theta plus 1. And underneath we're not going to do anything, we're just going to leave it as is. But now what happens is we are multiplying here, so we can eliminate this whole factor and that whole factor, and we're going to get secant of theta plus 1 remaining, which is exactly what we wanted to show. So that's proved. But like I said, be very careful here. Don't eliminate ones or secants. You cannot do that because these are attached with minus or plus. That means you can only eliminate the entirety of what you see here if you see the exact same thing down here. And we don't see that, so we have to factor to make that work. So that's a pretty easy way to go. And we're going to do this same problem 3 different ways. And that was probably going to be the easiest way. Here's another way to do it, working with fractions. We're going to do the same way, same problem, but we're going to do it the first way we did this by changing everything to sines and cosines. So we're going to make tangent squared into sine squared over cosine squared. And on the denominator, we're going to write 1 over the cosine, because that's secant, minus 1. So you can already see this is looking a lot more challenging than what we did the first time, than we did on the last one. So, but we're going to go through it, and you just have to be able to work with fractions. So what we do here, we're going to leave that alone. We cannot do a copy times flip until we've turned this denominator into one fraction. Now it's the subtraction of 2 fractions. We're going to put it together as 1. So the easiest way to do that, we just put it over the 1 over 1, and we're going to get a common denominator. Sorry, I'm not rewriting this, I'm just saving space. We're going to leave sine squared over cosine squared alone. In the denominator, we are going to get a common denominator of cosine times 1. If you know anything about adding and subtracting fractions, to get cosine to turn into cosine, we do nothing, so we're going to do nothing to the 1. That stays a 1. To change the 1 into a cosine, we're actually going to be multiplying by cosine over cosine. So we are going to get a minus, and this is 1 times cosine, and the denominator will also be cosine, so we have that. But now we have 1 fraction over 1 fraction. We can actually go ahead and do a copy times flip now. Sine squared theta over cosine squared theta. That's the copy times the flip. Now we're going to flip the denominator into cosine theta over 1 minus cosine of theta. And we look and see if there's anything that can be eliminated, and we can divide out a cosine of theta and one of these, which is we're going to get left with sine squared theta over cosine theta times 1 minus cosine theta. And it looks like we are kind of stuck. One thing you're not going to want to do, you typically don't want to distribute things like this on the denominator unless you have to at the end if you have nothing else to do. But sine squared, you should recognize that we can write the identity I'll write in a different color so you don't get too confused. Sine squared theta plus cosine squared theta equals 1. We can manipulate that identity by subtracting cosine from both sides into 1 minus cosine squared theta. What that means is we can make the substitution of 1 minus cosine squared theta. We're getting closer. It almost looks like we can make an elimination with these two, but we cannot because that's squared and that's not. So we're going to do what we did on the last problem, and we're going to factor it again. 1 minus cosine theta times 1 plus cosine theta. In the denominator, we're going to leave cosine of theta times 1 minus cosine theta. And these are going to eliminate, and we're going to get 1 plus cosine theta over cosine of theta. And it doesn't look like we've done what we need to do, but we're going to finish it off anyway, because what we can do now is we can split these fractions up. 1 over cosine theta plus cosine theta over cosine theta. And we all know 1 over cosine is the cosecant. I was about to write secant. I should have written secant. That is wrong. This is the secant of theta. I'm too smart for myself. Or the other way around. I don't know. And then cosine over cosine is 1. But either way, we get secant of theta plus 1, and that is exactly what we started with. Okay guys, this is a continuation of my last video about verifying trig identities. I rewrote something wrong, so I had to start over. But I'm going to redo this problem using conjugates to solve a problem like this or to verify this identity. Basically, you do this when some people do it right away. Like if you did this right away, it makes this problem a little bit easier. But some people don't think about it till the very end, and they get stuck on a fraction. You always do this with a fraction you can't eliminate. You might run out of ideas, not know how to cancel anything or factor anything, so you try conjugates. It can get you through a situation where you can't do anything else, so maybe conjugates actually set something up that you can factor out or cancel out. So what you want to do is pick one of the two, in this case secant minus 1, and you're going to multiply it by its conjugate, secant of theta plus 1. You're going to do it to the numerator and denominator. And just notice that the conjugates have to be opposite signs. So this was secant minus 1, we're going to do secant plus 1. Basically, this is the difference of squares factoring rule, but it's that rule in reverse, so it's actually going to undo itself. So what happens is you leave the numerator alone and you do the multiplication. But you're not going to distribute unless we have to at the end. We don't know what else to do, we'll distribute it. But you typically don't want to do that at the top. But when you do the conjugates, you definitely always want to distribute. That's the whole point of this. You're going to do secant times secant, and that's going to create a secant squared. And then when you do secant times negative 1 and positive 1 times secant, this is going to make a negative secant right here. This is going to make a positive secant. When you combine those, they're going to create 0, so they're going to be gone. Then the last thing we're going to do is we are going to multiply the 1 and the negative 1. And that's easy. That's going to be minus 1. So we're going to eliminate down to that, which didn't look like it helped us a whole lot because we still can't we still can't divide any of this secant stuff out because that's squared and that's not. But what we can do is we can look at tangent squared right there, or even secant squared minus 1 for that matter. That'd probably be easier. We can use the Pythagorean identity of 1 plus tangent squared. I'm writing it in a different color. This is just a little side work. We can use 1 plus tangent squared equals secant squared. We can rewrite it to make it look like that if we subtract the 1 from both sides. And we're going to get tangent squared equals secant squared minus 1. What that means is we can rewrite the numerator as is. Nothing new there. But we can make a substitution of secant squared minus 1. We can change that to tangent squared, which allows us to divide out the tangent squares, giving us secant of theta plus 1, which is what we wanted to prove in the first place. One thing I have to remind you, what you cannot do here, this is like a question mark. What you don't ever want to do is assume equality, even though we know it's equal. you can't use the fact that it's equal to prove that it's equal. So what you cannot do is treat this like an equation and multiply both this side and that side by secant plus 1. That's not allowed, so watch out that you don't do it. But by working this side down until we got that side to show up, we've effectively proved it, and that's how you use conjugates to help you verify trig identities. And there's Michelangelo saying cowabunga.